Okay, so thanks for the introduction, Ricardo. Okay, so the work I'm going to present you concerns the data fusion of cartographic products to produce a geostratigraphic map, in this case for the Tsiolkovskiy crater. So Tsiolkovskiy is a late Imbrian complex crater formed by an oblique impact coming from the northwest direction. And it is characterized by a mirror filling and a well-preserved central peak on which were detected both olivine and pure stanartosite. Recently, for Tsiolkovskiy were produced both a morphostratigraphic and a clementine-based map. The correlation of the two maps allowed the first correlation between the different geologic units and the compositional information that can be derived from the clementine coloration mosaic. So that we have a large smooth basaltic plain surrounded by noritic anorthosites and anorthosites scattered on the highland soil material correlated with the distribution of the hummocky floor material and their slope material. In particular, on the basaltic plane, we can distinguish three different color hues that by means of age determinations were correlated with three different flooding events occurring over 700 million years. As concerns the compositional differences of these events, both the clementine coloration mosaic and the titanium abundance estimation base map return that after the first effusive event, there was a slight increase in titanium content, progressively depleting during the last effusive event. So to further investigate the compositional properties of the area, we proceeded with the definition of spectral units, a reliable method that helps in summarizing the information enclosed by a set of spectral parameters by processing them at the same time. So for this work, we use global multispectral data acquired by the MCube instrument. And the spectral parameters that we took into considerations are the reflectance at 0.54 micron, the band depth at 1 and 2 micron, and the spectral slope between 0.54 micron and the maximum of the first and second shoulder of a band depth at 1 micron. So now let's see an example with a reflectant at 0.54 micron. What we did is we took the histogram distribution and divided it into intervals from low to high values. Here you can see the different pixels in different colors according to the different threshold intervals. And in the table, you can see the different intervals with a range of values. We did that for all spectral parameters. Then all threshold intervals were intermingled and all unique combinations resulted in 10 different spectral units. And this is our spectral units map. So now to proceed with our mapping data fusion and to realize, to produce, sorry, geostratigraphic map, namely a more complete product, including both morphologic, stratigraphic, and compositional and mineralogical information that can be derived from spectral data and derived products, such as color base maps, prism per component analysis, color ratios, spectral units map. We took our morphostratigraphic map and traced new contexts based on the spectral units map to integrate the spectral information. Using for the new context as the starting base, the context previously digitalized for the clementine-based map. Our final product is a geostratigraphic map, including both morphologic, stratigraphic, and compositional information. And in particular, on the smooth floor, we can see beautiful colors. We can see again that the smooth floor is characterized by three different spectral units that are each correlated with a clementine basaltic plane unit and refer to a different age and composition. All remaining spectral units have a more widespread distribution. So to further investigate the composition and properties of these units, we retrieved the reflectance spectrum. In particular, we can see that our red, green, and blue mirror units present the lowest reflectance spectra and the strongest absorptions at 1 and 2 micron. Shallower absorption bands characterize the unit 10 in coral and unit 6 in magenta. In particular, unit 6 is characterized by an intermediate reflectance spectral, indicating the contribution of iron-bearing mineralogical phases, while unit 10 is characterized by a higher reflectance spectrum, indicating a significant contribution of plagioclase, as also suggested by an absorption at 1.3 micron. All remaining spectral units present fainter absorptions and intermediate to high reflectance values. To further investigate also the composition analysis through the comparison with laboratory data, we plotted within the range of 1 and 2 micron the average derived band centers for calcium-free, low calcium, and high calcium synthetic pyroxenes. And we plotted also the values for our spectral units, the full colored dots. What we can see is that our three MER units, the magenta and coral unit still presenting strong absorptions, and the maroon unit cluster in between the low calcium and high calcium groups, with a red unit presenting a shift toward a more augitic composition. 4 units instead present a shift of a band center 1 forward the longer wavelengths, indicating the contribution on another component. So to investigate if olivine could be responsible for this shift, we then calculated the band area ratio and plotted it versus the band center 1, superimposing the olivine pyroxene mixer strands by Clutis et al. And Zhang and Clutis. What we can see is that our three MER units cluster in proximity of a trend, and the red unit associated with the intermediate flooding event characterized by a slight enrichment in titanium presents a shift toward the olivine-dominated end member, suggesting a slight enrichment, also in this case, of olivine. This is even more true for the coral unit, the spectral unit 10. In this case, both the presence of strong absorptions and the shift toward the shorter wavelengths of a band center 2 exclude the contribution of glasses and spinel. Therefore, olivine seems a measured contribution to this shift of a band center 1. This, coupled with the higher reflectance spectrum indicating plagioclase, suggests a troctolithic composition. Then we have spectral units 6 and 10, so magenta and maroon units that present a shift, an increase of the band area ratio, indicating a strong contribution of opaque mineralogical phases and glasses. And then again, we have for the units, the units 4, 5, 9, and 8, so yellow, cyan, purple, and dark green, that present both an increase of the band area ratio and of the band center 1. Therefore excluding the presence of olivine. In this case, they still present, even if faint, absorption bands that indicate the involvement of a mafic component, but glasses likely mask their contribution. So, to sum up, what we obtain is a M-cube derived spectral units map with 10 spectral units. Spectral units 1, 2, and 3, that are the MER units, are correlated with a distribution of the Clement and basaltic plane unit, and therefore to a different age and composition. They also present the lowest reflectance slopes and the strongest absorption bands, and they completely define the smooth material of the floor, and therefore a basaltic composition with a very low to low titanium values. Spectral units 7, 8, and 10 show instead a high reflectance spectra, indicating a strong contribution of plagioclase. Spectral units 7 and 8 in particular reflect might reflect the presence of an orthositic gabbros to gabbroic anorthosites, depending on the relative abundance of plagioclase and clinopyroxene, while the detection of olivine for the spectral units 10 suggests the presence of troctolite. Finally, spectral units 4, 5, 6, and 9 are characterized by intermediate reflectance spectral and fainter absorptions, with the exception of spectral unit 6 that indicate a measured contribution of iron-bearing mineralogical phases, and they might reflect the presence of gabbroic rocks. And here take it by heart. It is just an example to show you the compositions. And so to conclude, we can say that the new geostratigraphic map produced for Tsiolkovskiy crater takes a step forward in the roughness of moon geologic maps by integrating also the compositional information that can be derived through a laboratory comparison with laboratory data. Overall, the impact leading to the formation of Tsiolkovskiy occurred on a highly anorthositic crust characterized by scattered pockets of gabbros and troctolites. And the impact exhumed material from the lower crust up to more or less 30 kilometers, but it was not sufficient to exhume material from the olivine orthopyroxene-dominated upper mantle. Indeed, we did not detect orthopyroxene. Sorry, I'm really fast, but I concluded. And here the bibliography if you want.
Okay, thank you, Gloria. We have plenty of time for questions. I will not make anyone since I'm co-authoring. So is there any question? Okay, while you think, I have a comment meanwhile.
Riccardo.
Yeah, that is it. Ah, okay.
Christian Brinkrink, Radboud Radiolab. This is very interesting because, of course, from a radio astronomy point of view, we would love to make use of Tsiolkovskiy crater to put radio antennas down. And in this context, we are interested in the close to the surface, the structure of the subsurface layers present and how rough, for instance, different rock sizes might be distributed there. Is there any information you might be able to derive on that front, or is that scale not really?
So about the surface slopes, so you mean?
So specifically the crater floor, and then the layering at, I don't know, up to several hundred meters below that.
Okay. The surface of Tsiolkovskiy is for sure really smooth. I produced also slopes maps, but in this case I didn't show them. And as concerns the layering, we can just infer how it is divided because we don't have information about it. Oh, yeah. It is hard to see, but in this case, but you have the TV, so it is in this case better for you to see. In this section, we have made a sketch of how could be the layering below Tsiolkovskiy, considering also the different effusive event. So you can take a look, and for sure we don't have sufficient data for assessing that it is correct, this interpretation.
Any other question? We have one question there.
Jeff Gillis-Davis from Washington University. If you had a CLIPS mission available to you, where would you want to land and what kind of hypothesis would you test within Tsiolkovskiy?
Okay, I'm Alpha Deep, so I suppose I heard your question. Where I would like to land, like a red.
Yeah, where would you like to land?
Okay. So in this case, I also analyzed, I didn't show it in this work, the southern part of the peak, near the detections of olivine. Well, the detections were made on the peak, on the highest heights of the peak. But it is interesting because there are many rolling trails indicating that many boulders fall from the peak to the smooth floor. In that case, it would be also interesting to land a mission in that area to be able also to collect samples directly from, without hiking the peak, to collect them directly on the floor. And it will be also possible to reconstruct the detachment area of the boulders by following the rolling trails.